Hello, just a quick little video to tell you about the converse of what we just talked about. Here we have a weak base and it's being titrated with a strong acid. And I'm very sorry I don't have an example problem in PowerPoint that I can use to make a video, but we'll do examples in class. But generally, this is just kind of opposite of what we did before. And so here's what our titration curve looks like. It basically looks like you flipped the curve from the weak acid titration upside down. Now we have several different equations at play when we do the titration. When we start, you just have a weak base. And so the pH is just determined by the base ionization equation. So you have your weak base, put it in water, it makes its conjugate acid, and then hydroxide. It's a base, it makes hydroxide. And so this is the only equation you need before you start, which again, this will be just like when we did weak bases. Then, when you add acid to this, you're going to convert the base to its conjugate acid. So you convert B to BH plus, and this is because the base plus acid makes this conjugate acid, right? So this is the base acid neutralization equation, and this is the strong one. It's a forward arrow, and it serves the purpose of turning your weak base into a buffer. Then when you're in here, you're in the buffer region. Now at the midpoint of your titration, halfway to the equivalence point, analogous to what we did with weak acids, your pOH is equal to your pKb, and so then 14 minus that would give you your pH. Or another way to think of it is your pH is equal to your pKa of the conjugate acid. Either one works, gives you the same number. All right, now when we keep going, we get to the equivalence point. Just like with weak acids, the hydrolysis of the conjugate thing makes the endpoint not pH 7. So here you have the conjugate acid of your weak base, and that is functioning like an acid because it will hydrolyze water. And so your pH value here is less than 7 because it's acidic. And again, only your conjugate acid from that weak base remains at your equivalence point, and so then that drives your pH to be acidic. Then, just like before, after the endpoint, any extra strong acid that you add just hangs out in solution and it makes it more acidic. And it's just like adding an acid to water. You have to think about the dilution. You have to think about how much has already been neutralized. And then beyond that, then you just find the pH. Now, one last thing I want to show, I think this is cool, honestly, that's why I show it, is that if you have a polyprotic acid and you're titrating it with a strong base, or this would be true if you had a poly base and you're titrating it with a strong acid, you get several different equivalence points in a row. And so basically you just kind of stack them. You just do this several different times and then you'll get a pH titration that looks like this. I wanted to show you this because sometimes these polyprotic acids are useful in biology and biochemistry, and so you might see these plots. And so just keep that in mind. If you were trying to use this as a buffer, somewhere around one of these midpoints is a good place to use it as a buffer. For this particular acid, phosphate, you could use it as an effective buffer here. This happens to be around pH 7, which is really nice for biology things. You can also use it as a buffer in this region if you wanted something really acidic. For this particular acid, I don't know if I'd use it as a buffer out here because it's just not so effective. But anyway, so that's all we have for this video, and we'll do some examples of the weak base titration in class. And just remember to do everything base-like instead of acid-like, and you'll be okay. All right, thanks for watching.